Welcome back to Science Click. Today, spin. At the fundamental scale, matter is composed of particles that exist in different versions and which make up everything around us. Particles have properties, a mass or an electric charge for instance, which define their behavior. In 1922, the Stern-Gerlach experiment identified a new property of particles. When sending a beam of silver atoms through an inhomogeneous magnetic field, it splits in two. Half the particles are deflected upwards, the other half downwards, as if there were two types of electrons reacting differently. We first imagined that the electrons in the atoms behaved like tiny marbles spinning on themselves, thus generating a small magnetic field like an electromagnet. This would explain why they are deflected, but not why the beam splits in two. The electrons would be more or less aligned with the magnetic field, and therefore more or less deflected. It was later calculated that this explanation would require electrons to rotate faster than light, an absurd result. Today, quantum field theory, our most advanced model, describes particles as dimensionless points. They have no size, and therefore cannot rotate on themselves. In short, particles seem to have an intrinsic property, just like their mass or charge, which we call spin. In this video, we will try to understand the origin of this property and why the electron beam splits in two. Although it is often held to originate from quantum physics, we will see that spin rather comes from the geometry of space, rotations, and group theory. A group in mathematics is a set of operations which can be combined or reversed. For example, the set of quarter-turn rotations 0 degrees, 90 degrees, 180 degrees and 270 degrees forms a group, a set of operations that can be combined or reversed. Groups are very useful for describing the symmetries of an object. This gemstone, for example, is symmetric under this group because it does not change appearance after any of these four rotations. This next stone, on the other hand, is not symmetric since it changes appearance depending on the orientation. This particular group, made up of four rotations, is called by mathematicians Z4. Which simply means that it is generated by an operation which cancels itself when applied 4 times in a row. Of course, this is just one example of a group among many. The hours on a clock are described by Z12, since this group returns to the starting point after 12 rotations. There are also infinite groups like Z squared, which contains all displacement of this checkerboard, and even continuous groups like that of all rotations between 0 and 360 degrees. We call it SO2 because it describes the rotations in 2 dimensions. The SO3 group describes the rotations of space in 3 dimensions. And in special relativity, we study the group SO3,1, which describes the rotations of spacetime with 3 dimensions of space and 1 dimension of time. However, let's focus on our first example, which is simpler and contains only 4 rotations. To understand how a group can manifest itself and act on objects, let's consider these 3 gemstones and look at how they transform under the action of rotations. The rotation group has no effect on the blue stone. The red stone, on the other hand, changes, and each of the 4 operations generates a new, unique appearance. Finally, the green stone changes after the first rotation, but returns to its initial state as soon as the second rotation occurs. The blue stone is always in the same state, the red stone can adopt one of 4 states, and the green stone one of 2 states. Let's now imagine that these stones represent particles. As physicists, we know neither the appearance nor the structure of particles. They are fundamental objects, elementary building blocks without dimension. However, we know that some particles can adopt different states depending on their orientation. And even if we do not perceive these different states at our scale, we can imagine that they would have some sort of physical effect during experiments. Let's invent a new abstract space, the state space, in which we plot each state that a particle can adopt. Each particle has its own state space. Let's now rotate the red particle by 90 degrees. Its state has changed. We can say it too has rotated in the abstract space of states. For the same 90 degrees rotation, the state of the blue particle does not rotate, while that of the green particle rotates twice as much. The key idea is that we can associate to each rotation in space an abstract rotation in the corresponding state space. This construction allows us to distinguish the behavior of the three particles. The state of the blue particle rotates 0 times. That of the red particle rotates 1 time. And that of the green particle rotates 2 times. We call this property the spin number. The spin number describes how rotations in physical space are represented in the abstract space. The blue particle has a spin number of 0, the red particle of 1, and the green particle of 2. We say that these are 3 different representations of the rotation group. The spin number is just a label to classify different behaviors when we apply a rotation to an object. This bottle has spin 1 because its state changes as fast as space. This button has spin 0 because its state doesn't change. And this playing card spin 2 because it comes back to its initial state twice as fast as space. To put it simply, the spin number of an object measures how fast it comes back to its initial state. In order to make calculations and predictions, physicists want to model the world in the language of mathematics. Instead of buttons, bottles, or playing cards, they look to mathematical tools to describe objects. A spin 0 object will generally be modeled as a point or a number, which has no orientation and always keeps the same state. A spin 1 object will generally be modeled by a vector, a sort of arrow which changes when it is rotated. Finally, a spin 2 object will usually be modeled by a rank 2 tensor, which can roughly be thought of as a double vector, and which returns to its state after only 180 degrees. So far, we have focused on the group Z4. In reality, physicists are interested in all possible rotations of spacetime. Still, the idea remains the same. If we know the various representations, ways in which rotations can affect an object, we have a catalogue of mathematical tools to model the universe. This is precisely how physicists have described particles. Some particles have spin number 0, like the Higgs boson. Its state doesn't change, and we therefore describe it by a field of numbers. Others have spin number 1, like the photon which constitutes light. Light has a directionality called its polarization, which only returns to its initial direction after 360 degrees. It is this polarization which allows polarized lenses to block certain light depending on its orientation. Light is described by a vector field, the electromagnetic field. Finally, the graviton, the still hypothetical particle of gravity, would have a spin number 2, because in general relativity, we describe gravity by a field of rank 2 tensors, which return to their state after only a 180 degrees rotation. This spin 2 property is found in the very structure of gravitational waves, which deform space in 2 perpendicular directions, with a symmetry of 180 degrees. In short, The spin number indicates which mathematical tools can be used to describe particles according to how they react to rotations. But what about electrons? And more generally fermions, the particles of matter? We often hear that these particles have neither spin 0, 1, nor 2, but 1/2. How can something have spin 1/2? If we imagine a new gemstone with a spin number 1/2, this means that each rotation would generate only half a rotation in its state space. It would thus require not one, but 2 full turns to regain its initial state. Of course, this seems absurd in classical physics. All objects must remain the same after a 360 degrees rotation. Still, these spin-half particles do exist, and even make up, within atoms, all matter that surrounds us. To understand, we will have to delve into quantum mechanics. The core of quantum mechanics is the superposition principle. To understand it clearly, let's make an analogy with a coin. In classical physics, a coin only has 2 possible states, heads or tails. However, in quantum mechanics, as long as we don't observe it, the coin can actually be in a quantum superposition, a state involving both heads and tails, with probabilities. It is only when we observe the coin that the universe will have to collapse at random between heads or tails, according to these probabilities. Of course, this is just an analogy. This phenomenon does not occur for a macroscopic coin, but it does occur at the scale of quantum particles. To model quantum superpositions, we once again use an abstract space, in which heads and tails are just 2 axes, 2 directions. Each superposition is a sum, which involves heads and tails in arbitrary proportions. This state, for instance, corresponds to the sum heads plus tails, this one to the sum 2 heads minus 3 tails. Heads and tails act as coordinates in this abstract space, and all superpositions are potential states that the coin could adopt before it is observed. When we observe it, the probability of getting either heads or tails depends only on the direction of the coin's state. The more it is aligned with the tails axis, the more probably we'll get tails, and vice versa. The one thing that's worth noting is that the probabilities of getting either heads or tails are the same whether we consider one state or its opposite. Whether the state is directed in one direction or the other has no impact. Its alignment with the heads and tails axes remains the same, and the probabilities for these results are therefore the same. The 2 opposite states actually represent the same reality, and it is impossible to differentiate them with any experiment. The state plus heads, for instance, is physically equivalent to the state minus heads. It is this subtlety that will finally allow us to understand spin 1/2. Let's return to our example one last time. We saw that an object with spin number 1/2 was impossible in classical physics because a full turn would bring it to the opposite of its initial state, which is absurd. However, if the object is quantum, this is not a problem anymore, precisely because the opposite of a quantum state is physically equivalent to it, although mathematically different. The idea of a spin-half object is therefore allowed within quantum physics. We call the mathematical tool that models it a spinner. It is an abstract entity which requires 2 rotations of space to return to its starting point in the state space. This is allowed because after one full turn, although it is now in its opposite state, the spinner physically describes the same initial situation. We might think that spin-half objects aren't very interesting, given that they still come back to the same physical state after a full turn. However, there is actually a difference between spinners and the other tools we've seen so far. If we consider one state and its opposite, These are physically equivalent, but they become different in a superposition with another state. And if we imagine a field of spinors in which waves propagate, the superposition of two waves will be different if we replace one of the two waves by its opposite. Spinors therefore do have interesting properties that differentiate them from other objects. With all these notions, we can finally understand the spin of an electron. Electrons have spin number 1/2. This means that they can be modelled by a field of spinors, which return to their initial state after only 2 complete rotations. If we pick an electron at random, it will have a state pointing in one direction of its abstract state space. We call this its spin state. Physicists have named the axes of this space up and down because electrons in these states are deflected upwards or downwards in the Stern-Gerlach experiment. If we rotate the electron, its spin state will also rotate in its abstract space, but only half as fast because its spin number is 1/2. A spin-up electron becomes spin down after 180 degrees. After a full turn, the spin-up electron has reached the opposite state, minus up, but this is physically equivalent to the initial spin-up state. These two states are analogous to the heads and tails axes of the quantum coin, and during a measurement, the electron will collapse at random onto one of these two results, either up or down. It is this property that the experiment highlighted back in 1922. Understanding why such particles behave as if they were spinning on themselves is quite technical and beyond the scope of this video. It boils down to the fact that angular momentum, which measures how much an object is spinning, can be calculated by looking at how an object's state changes after a small rotation. And since the spin number characterizes how fast a particle's state changes during a rotation, it therefore acts as a sort of angular momentum internal to the particle and generates similar effects to a spinning motion. It is crucial to understand that the spin state of an electron, up, down, or a superposition of the two, is not a direction in space, but an abstract direction in a mathematical space invented to describe the particle. In fact, so far we have visualized rotations in 2 dimensions, but our space actually has 3 dimensions, in which we can change orientation. The abstract space which describes the spin of an electron, however, only has 2 dimensions, up and down. They are 2 completely different spaces, linked only by the fact that each rotation in one is mapped to a rotation in the other. To be perfectly exact, quantum mechanics does not use real numbers but complex numbers to describe quantum states, which makes this space harder to visualize. Let's avoid getting lost in details and summarize everything we have seen one last time. Particles have an intrinsic property called the spin number. The spin number characterizes how fast the state of a particle changes when we rotate it in space. Some particles have integer spin numbers 0, 1, or 2, for example, but quantum mechanics also allows the existence of particles with half-integer spin, in particular 1/2, which need 2 rotations to regain their initial state. When we measure the state of such a particle, it randomly collapses onto one of the 2 axes of its abstract space, explaining why the beam splits in 2 in the Stern-Gerlach experiment. Finally, a few years later, in 1928, Paul Dirac became interested in the behavior of spinors when we add the dimension of time in the context of relativity. When we change our reference frame, which amounts to rotating spacetime, a spinor rotates accordingly within its abstract space. However, it turns out there are 2 possible behaviors. It can react either in one direction or the other. Mathematically, a spinor somewhat behaves like a square root. There are 2 of them, one positive and one negative. In the same way, there are 2 different types of spinors reacting in opposite ways in the direction of time. they correspond to particles and antiparticles. In this way, Dirac mathematically predicted the existence of antimatter.